All right, so starting with 5.3, we're going to be looking at polynomial functions, getting the definition, talking about different standard forms for different degrees of polynomials. So a polynomial in one variable is going to be a little bit different than what you guys saw in 5.1. 5.1 we saw a lot of like x's and y's and a's and b's all combined into one. What we're going to be looking at today is just polynomials that only have one variable, just an x, just an a, whatever it is. So a polynomial in one variable is an expression of the form and then it looks like this. A, so this is going to be a little confusing, but I'll explain. So a sub n times x to the nth. So with this a sub n, that represents a constant, and then x to the n, so that's going to be the biggest number, you know, x to the fourth or x to the fifth, whatever the biggest one is. And then plus a sub n minus 1 times x to the n minus 1. So if this one starts out as 5, this next power is 5 minus 1, which is 4. And then this is just the coefficient that's attached to that one. And then on and on and on, all the way down until we are in front of, you know, x squared, x to the first, and then we just have some constant, which we call a sub 0. All right, so sorry, that got a little snuck in there. So the second coefficient times x squared plus the first coefficient times x to the first, and then plus just the constant. So that is kind of the standard form for any parabola. All right, so standard form is when the values of the exponents are in descending order. So if I ever ask you to take a polynomial in one variable and make sure that you write it in standard order, what that means is that you're starting with, like, you know, say the biggest power is 5. You're starting with x to the 5th, then x to the 4th, then x cubed, etc., etc. All right, and then we've got a couple other things that we can write down here. We also have something called the leading coefficient, and the leading coefficient is whatever is in front of the largest power. So that would be whatever this is right here. So the leading coefficient, and again, that is the coefficient of the first term if it's in standard form. Okay, so we are going to make a little chart here, different polynomials, different degrees of polynomials. So I'll give you guys some examples. So an example of a constant polynomial would be something like 12. Literally just a constant, and that's it. And so if you just have a constant and there are no variables at all, the degree of that polynomial is 0. Because there's no like x to the first or anything like that. So in this example here, the leading coefficient would just be the 12, because even though this doesn't even have a variable, it's still the largest degree. A linear example would be something like 4x minus 9. So a linear function forms a line. We've seen these examples before. 4x minus 9, we can talk about its slope, we can talk about its y-intercept, and we know that something that starts out looking like this, the equation, ends up being drawn as a line. And so the degree here, we have an x to the first, and so the degree is 1. In this example, the leading coefficient is 4, because the largest term is the x, and the coefficient attached to it is a 4. Okay, now keep in mind, these are just examples of different types of polynomials. An example for a quadratic would be a 5x squared minus 6x minus 9, or something like that. The degree with this one, the largest power here is a 2, so the degree is 2. The leading coefficient is whatever is attached to the x squared, and that would be a 5. Next one, a cubic example. Cubic is, you know, something cubed would be raised to the third power. So cubic function would be something raised to the third power. So let's say like 8x cubed plus 12x squared minus 3x plus 1. Okay, so here the largest power is a 3, so the degree of this polynomial is 3, and then the leading coefficient is whatever is in front of the x cubed, and so we write an 8 right here. Okay, a quartic function. A quartic might make you think of like quarter, and that's splitting something into fourths. So quartic is the fourth power. So maybe we have like negative 2x to the fourth plus 7x squared. Now notice you don't have to have one of each. It's not like I have to have an x cubed and I have to have an x. It could be something as simple as this. Here the degree is 4, that's our largest power, and the leading coefficient would be a negative 2. Okay, and finally a quintic polynomial. Think of like quintuplets. That prefix means 5. So this is something to the 5th power. So maybe we have like 3x to the 5th minus x to the 4th plus 7x squared again. This degree is 5, and the leading coefficient is a 3. Okay, so those things are pretty easy to identify. So stating the degree of a polynomial and then identifying what the leading coefficient is. So let's look at this example right here, number 1. Now the directions read state the degree and the leading coefficient. If it is not a polynomial in one variable, explain why. Okay, so let's look at this first example here. So if we look at this one, we've got 5x cubed minus 4x squared minus 8x plus 4 over x. So remember what we had when we were doing in 4.1. We were trying to identify, first of all, whether something even was a polynomial or not. And one of the things that I told you guys to watch out for was anything that has variables in the denominator. So this is not a polynomial in one variable. 4 over x has an exponent that's less than 1, and so this is not a polynomial. So not a polynomial. And what we'll say is that 4 over x has a degree less than 1, or I guess less than 0. Because remember, since this x is in the denominator, it's technically an x to the negative first, and that exponent is something that's less than 0, and we're not allowed to have that in a polynomial. Okay, let's look at a couple more examples, same thing. Okay, so part B. This one is a polynomial. All of our exponents are positive integers. We don't have any square roots. We don't have any variables in the denominator. And so here we're just going to try to pick out what our leading term is. So this guy right here is the leading term. It has the largest exponent. And so the degree is whatever the largest exponent is. So this is a 6th degree polynomial. And then your leading coefficient is whatever coefficient is attached to that leading term. So the number attached to that leading term is a 5. Okay, so that's all you're answering for these. Very, very simple. Next one, we are answering the same thing. Okay, so but this one be very, very careful because people automatically want to look at this first term and say, okay, well, that must be the leading term, so my degree is 4. Make sure you're looking through the whole thing. This one is not in standard form. This one is. Your degrees are going in descending order as you go down the polynomial. This one is not in standard form. We've got an x to the 4th, then an x cubed, then an x to the 6th, and then a constant. This x to the 6th is your largest term right here. And make sure you're paying attention to the fact that there's a negative in front of it. So your degree is, once again, 6. This one is a little bit different. We needed to be very, very careful in looking at the order of the polynomial. Okay, our leading coefficient here, again, is the coefficient that is attached to that x to the 6th. And because we are going to be very careful in remembering the negative, we now know that that is a negative 1 that's in front of the x to the 6th. If it's just an x to the 4th or x to the whatever and you don't see a constant, it's either 1 or negative 1, depending on the addition or subtraction. Okay, so those are pretty easy. Now let's talk about functions. It's a little bit different than just a polynomial. A polynomial function, you've got like that f of x notation. So functions, we have, it's a continuous function that can be described by a polynomial equation. Okay, so a continuous function and what a continuous function means is that it's something that you can draw without lifting up your pencil. So that makes sense. I mean, the lines, the parabolas, we know what those look like. They're these nice smooth curves. So a continuous function that can be described by a polynomial equation in one variable. Now in functions, we don't ever mix and match variables. We always have just the one. Okay, and then a power function. These are the simplest polynomial functions where you only have one term. All right, so these simplest polynomials, these are of the form f of x equals just a and then x to the b. So that's our kind of standard form of power functions. So it's not a whole bunch of them strung together, not like a term plus another term minus another term minus another term. It's just one, just the power function, and then a and b are non-zero real numbers. Right? Okay, so we're going to look at a couple of examples here. So example 2, we've got sort of a story problem. The volume of air in the lungs during a 5-second respiratory cycle is modeled by this function. So this is what's known as a polynomial function. The left-hand side, that's our function notation. You know, sometimes we see like f of x or g of x or something like that. But v of t means volume as a function of time, t. And then it gives us this function. This is technically a polynomial function, even though we have some crazy coefficients here, these weird decimal values. It's in standard form because we have t to the third, then t squared, then t. There just doesn't happen to be a function here. They tell us v is volume in liters and t is time in seconds, and then we know it goes just for 5 seconds. Find the volume of air in the lungs 4 seconds into the respiratory cycle. All right, so what we're trying to find is we want to substitute 4 into the function because they want to know what the volume is 4 seconds into this cycle. And so t is 4, and so we plug that into this piece right here. So we want to know what v of 4 is. So we've seen this notation before. Just as a reminder, what we do when we replace this t with a number, first of all, we write it right there just for notation's sake. So v of 4 means take the volume function, plug in 4 instead of t, and then we're going to go up into this function, and every single place where we see a t, we're going to replace it with a 4. All right, so we've got our original function right here. Then what we're going to do is we're going to replace every t with a 4. Okay, so we've got that written down. At that point, we're just going to simplify it down. And these are weird decimals. I would never expect you to do anything like this out by hand. And so let me just walk you through really quickly how we would plug this into our calculator. All right, so new calculator page. I'm going to get this on the screen too. So we're just going to plug in this strand exactly the way it is. So negative 0.037. There's some sort of weird glare. There we go. 0.037, I can put the 4 in parentheses. And the way you do the third power is see where the x squared is. Next to the x squared, there's this little caret key, like the up arrow. And so you hit that button, and then it opens up an exponent box. And you can put any exponent in there you want. And we want the third power. Then plus 0.152. Oops. Make sure you hit the tab key and get out of that numerator or the exponent. Plus 0.152, and then 4 squared, plus 0.173, and then times 4. Okay, so when you hit enter, it'll give you a decimal approximation. So it is about 0.756. Okay, so we want all 3 of those decimals because these numbers all had 3 decimal places, so we want to make sure our answer is accurate enough. And then what we get is our final answer, and this is going to be in liters. And then we're going to finish today with example 3. These ones are actually really similar to what we just did here where we're doing this function notation stuff. So we are evaluating functions for variables and algebraic expressions instead of evaluating functions just for numbers. Like here what we did is we evaluated a function for a number. We took the function v and we plugged in the number 4 and we simplified it down. What we're going to be doing with these examples is we're going to work with functions, but we're going to be plugging in entire variable expressions. Okay, so we'll go through this first one nice and slowly, and then these are the last 2 problems that we're doing for today. It's just example 3, part A and B. Okay, so start with this piece right here. So g of 5a minus 2. Okay, so let's start with that. So g of 5a minus 2. What that means is the exact same thing that notation meant up here. What this notation means is we use my function v, which I had right here, and every single time I see the variable, I replace it with a 4. So the logic is the exact same right here. I start with my function g, which they gave to me right here, and every single time I see the variable, I replace it with a 5a minus 2. Okay, so let's at least set it up, and then we'll work on simplifying. So x squared, when I see the x, I replace it with a 5a minus 2, and then that gets squared. And then minus 5, and then here's another x, so replace it with 5a minus 2, and then plus 8. Okay, so there's lots of simplifying that needs to be done here. First thing I want to point out, you're going to see this pop up a lot in this section. If you have an expression like that that gets squared, remember that means you need to write it out twice and then FOIL it. Okay, and let's work on simplifying the rest of this. Here I'm going to distribute a -5. So -5 times 5a gives me -25a. And then -5 times -2 gives me a +10. And then don't forget I've got that +8 hanging on the end. Okay, so let's FOIL and then simplify everything up. So 5a times 5a gives me 25a squared. Outside I have 5a times -2. It's a -10a. Inside I've got the same thing. -2 times 5a gives me another -10a. And then last, -2 times -2 gives me +4. And then let's write out the rest of this. So minus 25a, and then here I have a +10 and a +8, so I can write that as 18. So my last step for this piece anyways is to combine up all of my like terms. All right, so let me write what I've got so far. So I have 25a squared. I have minus 10a minus 10a, so I'm at -20a, and then minus 25. So that is a -45a. I have a 4 and an 18, so that's 22. Okay, so that's where I'm at so far. Then I have to add it to this thing right here. So now let's work on that. So now 3, and then my last step will be to add them together, times g of 2a. Okay, so first of all, taking just this piece of it right here, I'm still going to go into my function g, and every time I see the variable, I'm going to replace it with a 2a. Then I'm going to multiply the whole thing by 3. So I'm going to put a 3 on the outside, big set of parentheses. I'm going to plug 2a in every time I see an x. So 2a squared, and then minus 5 times 2a, and then plus 8. Okay, so keep the 3 on the outside because of this 3 right here. I'm going to simplify this stuff all down. So 2a squared gives me 4a squared because I square the 2 and I square the a, minus 10a, and then of course plus 8. Okay, so last step here is to distribute that 3, and then I'm going to combine these up. So 3 times 4a gives me 12a squared. 3 times -10a gives me -30a. And then 3 times 8 gives me 24. Okay, so I found this piece. I found this piece. The very last step is I'm going to add them together. So I'm going to take what I got for this one, 25a squared minus 45a plus 22. That is one expression right here. And then I am going to add to that 12a squared minus 30a plus 24. Okay, so my final answer will be what I get when I combine up my like terms. So I have 25a squared plus 12a squared. That gives me 37a squared. -45a, -30a. That gives me -75a. And 22 and 24, that gives me 46. Okay, so that is my final answer. Let's do one more of these, and then we'll be all done. Okay, so part B. We want to find something very, very similar to this. They give us a function h of x. It is also a quadratic function. Okay, so we're going to fill in all of this info here. So we want to plug in a -4d plus 3. So h of -4d plus 3, we're going to plug it into this function h of x right here. So 2 times that quantity squared plus 5 times the quantity plus 3. Okay, so remember what that means is we're going to FOIL everything out. So we are going to take 2 and then we're going to FOIL this out. I can distribute this 5. So -20d, -15 plus 3. Okay, now let's FOIL. We can start to simplify. So I'm going to FOIL these two. Don't forget I still have a 2 on the outside. So -4d times -4d is positive 16d squared. Outside I have a -12d, inside I have a -12d, so that's a -24d, and then last, 3 times 3 is 9. Minus 20d, and then here I get minus 12 from the -15 and the 3. Okay, so a couple more steps on this one. I need to combine up, it's right here, so 2 times this quantity I get 32d squared. 2 times negative 24d, so minus 48d. 2 times 9, of course, is 18. And then here are my other pieces here. So minus 20d minus 12. Oops, sneaking that in there. Okay, so let's rewrite this, combine all of our like terms. So this is the only d squared, so 32d squared. I have a negative 48d and a negative 20d, so that leaves me with negative 68d. Then I have a positive 18 and a negative 12, so that leaves me with 6. Okay, so that is this first piece right here. Then I am going to do a negative 0.5 times h of d. Now h of d is super, super easy because all I have to do is plug in just d for this function right here. Okay, so negative 0.5, and then I just replace the x's with d's. So 2d squared plus 5d plus 3. Okay, and then multiply that by 0.5. So half of this, I get a negative d squared. And then here I get a negative 2.5d. Because I have 0.5 times 5, so half of 5 is 2.5. And then minus 0.5 times 3, so that's a 1.5. Okay, so last thing is I am going to combine those up. This time I'm just going to combine them. I'm going to add them because I already included the negative right here. Okay, so just combine up like terms. So I have a 32d squared and a negative d squared. So that's a 31d squared. Sorry, this is so cramped. Negative 68d and a negative 2.5d is a negative 70.5d. And a positive 6 and a negative 1.5. And that is plus 4.5. All right, so that is your final answer. Those ones are probably going to be the trickiest ones, so make sure you're going nice and slowly on those.